All right. Thank you to the organisers for inviting me to present at the workshop on event-based vision. My talk's about fusing frame and event data for high dynamic range video, and I'll be using stochastic fusion methods. So event cameras and frame cameras are highly synergistic in terms of what they measure and how they measure. So event cameras produce asynchronous events, temporally dense information, they have no image blur, they have high dynamic range. So against that, frame cameras are synchronous, so they don't provide asynchronous, so they come in specific times, so they're temporally sparse, they're spatially dense rather than temporally dense. They do get image blur, but they have adjustable exposure, so you can choose what part of the intensity spectrum that you want to expose for. And they do measure absolute intensity, which the event camera doesn't, and they are able to image static scenes, which the event camera is unable to image. So combining these two these two sensor modalities together, you should in principle be able to get it all. So images that are spatially and temporally dense, and so by that we mean that at any point in time you can download a full image, not that you are downloading images at multiple thousands of hertz. Images with high dynamic range in absolute intensity scale, so combining the properties of both of those sensors, and images that don't have blur, both with static scenes and highly dynamic scenes. And so there's a number of different ways of doing that. We're working on some fusion type techniques, and I guess before I go into some of the details, I just wanted to show you some of the results we've been getting for the wonderful DSEC data set that has come out of UTZ. So here on the top left is the frame. So that data set, everyone probably at this workshop knows about it. It has an event camera and an RGB camera on both the left-hand side of the car and the right-hand side of the car. So we've ignored the right-hand side of the car. We're just on the left-hand side of the car. And the two cameras there, the RGB and the event camera, are quite close together, and so they're able to actually be registered together. So we're registering event pixels and RGB pixels together. And so we can see the raw frame in the top left. We can see what the state-of-the-art learning-based reconstruction methods are able to generate out of that data sequence. And then on the bottom left, you can see what we're able to do with these data fusion methods. And I guess some of the things to pick out is the quality of the light pole, which is actually partly really due to the quality of the frame-based information there, because you can see here in the event information that light pole is not so well picked out, although it is visible in the ECNN. And then things like the texture in the road that we're able to pick out, which is clearly washed out in the image, so that's coming purely from the events. And then really, in a sense, here in the events, you can see you are getting the texture, but you're not getting the intensity, the structured intensity that's actually coming from the main image. So this is really high dynamic range reconstruction without blur. Here's another scene taken from the DSEC going through a tunnel. Here you can see with the Kalman filter, the asynchronous Kalman filter that I'm going to talk about today, it's able to resolve information here where the camera is completely washed out. So that's purely working on events pretty much. You can see in ECNN here it's able to resolve that same information, but it's doing it without any consideration of the true intensity. So this is very bright compared to the rest of the image. Here it's just all at the same sort of intensity. And we see here E2VID is simply failing. And that's one of the problems with learning-based algorithms, of course, is that, you know, when you run into a data situation which they haven't experienced or haven't been trained for, they can simply fail completely, whereas an algorithm that's based on principled stochastic methodology will never actually fail in that sort of situation. Of course, you can retrain E2VID. Probably what's happened here is there's too few events in the majority of the scene, so all of the events for the little window that's been reconstructed from most of them occur in this area where actually the light is. And so it's been unable to reconstruct by using a bigger spatiotemporal sort of window to compress the data. Then you probably get a better image. But that's all engineering that you would have to do to make that algorithm robust to these situations. This is actually an older data set, which just is we've put in to show the temporal interpolation. So this is the shapes data set from quite some time ago that, again, people have seen. And you can see here in the top left image the 2 frames printed, one in orange, one in green, to just show the multi-pixel displacement that you're getting between frames. And so here what we're doing is we're interpolating information in between the frames, and we're using the state-of-the-art, the double integral method here, which is essentially de-blurring the image and then doing a simple interpolation from the events. And here we're doing the principal data fusion that I'm going to talk about, and it's getting rid of some of the edge effects that you can see. I didn't draw that very well, but if you look in detail at these at this image, you can see that there's an edge of the old image that is sort of present in the reconstructed image, which we get rid of. This is a difficult data set for us to deal with because it's taken with quite an old camera, and the quality of the event data set isn't as strong, and so consequently very high noise level and actually quite non-Gaussian noise, which breaks some of the assumptions of our filter. So the fact we do good at all is very good. All right, so now I want to talk a little bit about how we go about doing this filtering, and so I'll take us through a little bit of a quick journey through continuous time filtering methods or linear filtering methods for event cameras, which is some of the work which I did with Cedric Shearlink over the last few years. And then we'll talk a little bit about the asynchronous Kalman filter that I want to talk about. So the principles of this work is that we treat the events in a slightly different way than many people treat it. So event, of course, is a quantized time signal where the change in intensity is quantized, but the time is not quantized. Of course, it is in practice, but it's so finely measured that in principle you can treat the time stamps that come with the events as a continuous signal, and the quantization in the intensity of the events as the main signal. And of course, what you get out of an event camera is this spatiotemporal block of data where events occur at different times, and you get the events trailing through space. So image reconstruction, the simplest way to do image reconstruction is this idea of direct integration, which has been around right from the start. So in that case, you imagine trying to reconstruct the actual output of the image, or the image at time t, in a pixel, just a single pixel, and you run along in time and you get an event. So you say, okay, I integrate up, I get another event, I integrate up again, and then you work through the time signal. And this red curve here is the intensity reconstruction of the pixel, right? Given that the pixel started out with intensity 0 at time 0. So of course you don't know the absolute intensity, you just know the change in intensity. So the way we treat events is slightly different from some people. Instead of treating this just as a discrete sequence, what we do is we consider these events actually as a direct delta function. So that's a continuous time function, which is a distribution, so that when you integrate a direct delta function, so if I integrate, delta of t minus tk dtk with an a here, what I get is a evaluated at time tk. So basically, when this thing occurs, it integrates out to 1, and it gives you the value of the function a that happened to be inside with it. So by creating this event stream and then integrating it, we get exactly the structure that you would get by reconstructing direct integration, which is nothing special in itself. But what it allows us to do is model the whole process of direct integration actually as a linear system. And this is actually conceptually quite an important step. So what we've got here is a signal, and this is a continuous signal. It's not a continuous output, but it's a continuous time signal. So at every time tau, there is a value of that signal. It just happens to be that the values are distributions, these Dirac delta distributions. And the output there is also a continuous time signal. So again, it can be sampled at any time. And I can take the Laplace transform of that equation and I get a standard transfer function representation of a linear system where I simply get an integrator, a 1 on S, for the integral that I'm looking at. So I can use this framework of linear systems theory to analyze this reconstruction process. And that's the principles that we use in our work. Now, the limitation of this, of course, is that event cameras are noisy things, and if you do direct integration, and that's all you do, then every time there's a noisy event, it's integrated and its history is kept in your estimation of intensity forever. So once there's a piece of noise, it gets integrated into your history, and actually the output of the pixel becomes a random walk, and so it becomes purely noise. And you can see that here on the right-hand side, where essentially this is what we're doing, direct integration. There's not much going on out here on the left. The bicycle rides across, a whole bunch of events happen, a lot of them are noisy, and the result on the right-hand side here is a bunch of noise. So you can still see the bicycle, it's still working quite well. You can even see that the wheel is clearly propagating through the image quite nicely, but it is generating a lot of noise, and after a little while all you get is noise, and unfortunately it's also pixel noise, so it looks like somebody's just wiped dirt on the lens of the camera. So the sort of thing you can do with this linear filtering framework is you can filter. You can just simply design a filter, and so an obvious thing to do here is take the low frequency noise here. Well, it's DC noise basically, in a temporal sense it's DC noise. And we can do a high pass filter. So we're only interested in things where events are actually occurring, and we want to get rid of everything that happens after a little while. And if you do that, you get this picture on the right-hand side where you can see here that we're doing quite a good job of eradicating the DC noise that you get. And so you can do that in a linear systems framework where you simply throw a high-pass filter at it and do this. So it's a very nice way of thinking about processing event cameras. So there's another nice thing about this framework is that there are different realizations of linear systems. So this realization of a direct integrator followed by a high-pass filter is one realization of a linear system. So you can imagine that there's a black box where you feed a signal in, you get a signal out, and inside there's a bunch of electronics or a bunch of computer code that implements a certain set of linear system components. Okay, and we can equally well implement it in this way where I actually use some feedback. So this is a feedback realization of the same high-pass filter that we saw before. And I won't go through the details, but if you work out the actual transfer function between the input and the output here, you get exactly the same transfer function that we would have got if we'd simply direct integrated and then put a high-pass filter on top of it. And the nice thing about this representation as compared to the previous one is it has an ODE systems representation, a very, very simple linear ordinary differential equation. It's an IIR response effectively that implements that system. So from that framework then we do what was my work with Cedric Shearling some years ago, where we said, well, we can actually build a complementary filter. So we've got our event stream that's coming in, and if we actually also have the output from a camera, then the camera is like a temporally low pass information of the true intensity of the signal that we're actually measuring. And so what we can do is we can modify the block diagram that we had before here. You can see that there's no input here in the feedback loop, and we can put in an input here which in a feedback loop acts something like the reference. So the low frequency reference that we're tracking, the E acts like the velocity information or the high frequency information that you want. And you can use this feedback loop to fuse the two. And we can see here that the E information gets incorporated in exactly the same way as before, and then we get this filter for the low frequency information that comes in as well. And there's an ODE representation, which is very simple. So to understand what these two filters are doing, they have frequency responses that look like this. So the low pass filter is, this is the Bode diagram that I'm showing here. So the frequency response of the low-pass filter is unity below alpha rads per second, and then it rolls off at 20 dB per decade above alpha rads per second, while the high-pass filter rolls on at alpha rads per second and is unity for high frequency. So you're really, the high-pass filter is actually this term here. And so what we're doing is we're taking the direct integral information that we want, then high-pass filtering it, and we're adding that to the low-pass filter of the intensity information, and we're trading the two off. And the point about a complementary filter is if you add the frequency responses of those two things together, you get unity the whole way through. So you're rebuilding a unity gain information across the whole temporal response of the signal, trusting the true image information or the frame-based data in the low frequency and trusting the event-based data in the high frequency. And this is a very nice framework to do filtering with, and it comes with the particular advantage that because it has this ODE, so we have this beautiful ODE, which is actually the implementation of that filter, and we can look at that ODE and we can solve it, and we can solve it exactly, right? So we can solve it on periods when there's no events. So the events, remember, are only direct deltas. So when there's in between events, this term here is 0, and you're simply solving a linear system with y is a constant input, okay? And so we can solve a linear system with a constant input exactly. And when an event occurs, then it all happens at that particular instance, tk, and so we can actually do an update for the event information that occurs. And so this filtering framework is asynchronous, it's computationally efficient, and it allows you to reconstruct the image state at any moment in time. So this has been a great thing, and we've done a lot of work with this. It still has a few limitations, and the best way of showing those limitations will be to take you through the process of the asynchronous Kalman filter, and at the end I'll show you a bit of data which compares the various different filters. So one of the really important limitations of the complementary filter is that there's a crossover gain that you engineer in it, and that gain is something that the engineer chooses, and it's not adaptively changed in the filter. So you can change it adaptively, you can come up with heuristic algorithms to change it, but effectively it's just a constant gain. And so a key question that we started asking a few years ago is, how would you actually go about adaptively tuning that gain to optimize the fusion between the frame data and the event data? So in particular, when the conventional camera is well exposed, then you should be trusting the intensity in the conventional camera response. You might still be wanting to deblur the conventional camera and do a few other augmentation steps, but the intensity in those pixels should be reliable, and you shouldn't be trusting the event camera. So similarly, where the conventional camera becomes either underexposed or overexposed, then you should be trusting the event camera response, okay, particularly in those situations. And that's something that is going to be critical in reconstructing high dynamic range images, because the conventional camera will do a reasonably good job in the dynamic range where it's effective, and then it will die on the ends of that dynamic range. And that's where the event camera will be able to rebuild in those zones. And by combining those two, as the conventional camera moves around and provides more information around the areas where the high dynamic range is being reconstructed, you ground the reconstruction of the event camera, and you get the good results that we've been getting. So the algorithm that we're proposing is this one here, and I'll go through some of the details as we flow on from here. But just very quickly, firstly, the core of the algorithm is simply a complementary filter, which is the same filter that I was just describing to you before. And the only difference between the standard complementary filter and this one is that we're actually using a time varying gain here. So the alpha that we're putting into this is time varying. So then we're using the theory of Kalman filtering to design the gain in real time. And so we're essentially solving a Riccati equation to design the optimum gain that we're going to use, and we do that in real time, and I'll talk a little bit about how that works. So in order to use the Riccati equation, we do need to build stochastic models of the noise for both the frame data and the event cameras, okay? And the other thing that we're doing to get competitive results is we're also looking a little bit at the low frequency data, and we're doing some frame augmentation. So a couple of things that we can do. One of them is we deblur. Another one is we do a little bit of temporal interpolation. And so they're actually quite important for overcoming limitations of the complementary filter. In particular, the complementary filter had a zero order hold, which was screwing up some of the temporal response of the system. So that's the main things that I want to talk about. The other thing that's I'm going to mention a little bit in this framework is this idea of spatial convolution. And one of the nice things about linear filtering is that you can exchange linear operations. So if I want to take my output and then I want to convolve that output with some kernel and generate an interesting output from that, then I'm going to, I can actually do that by shifting that convolution through into the input of the signal here in the filter, and I can actually convolve my events and convolve my low frequency information here and have that run in real time. So let me just talk really quickly, because I don't have really enough time to talk about this in detail, about some of the modeling aspects of what we're doing. So we need to start with a model of the noise. So this is the covariance. So it has to be, for a Gaussian filter, it has to be a Gaussian model. Kalman filter is a Gaussian model of the noise that's going in from the events. And so we model that in a mix of covariances. So we essentially add 3 covariances together associated with 3 of the processes that go on. So one of them is simply a process noise. So this is simply a straightforward Wiener process that we're just adding onto the event data. So it captures just the uncertainty of the events. We also have an isolated pixel noise that we add into the event. So when a pixel has been isolated, it's more likely to be noisy. So this is a standard noise model that's used in many of the camera noise reduction algorithms. And we also add a refractory noise model, so that if the time between 2 events becomes very, very short, down close to the refractory period, then we increase the expected noise to try and capture the fact that there's likely to have been pixels events missed in the intermediary period. So we have a fairly simple but fairly effective noise model that captures a lot of what's going on. So we also have to capture the noise in the RGB camera, and digital RGB cameras are actually pretty good. So they have a base level of noise, but then they tend to be pretty reliable above that base level of noise across the intensity range in which they're operational. And so what you see here is an experiment we've done where we varied the exposure time for the RGB camera with a constant intensity and measured its response in the log scale. And you can see here the standard response. And what we're really interested in an event camera is capturing, in high dynamic range applications, that we're working about, is capturing what goes on in these extreme cases, right? So what's going on in these zones right at the ends of the intensity of the camera, right? So the camera is going to do a pretty good job out here where the pixel response is fairly linear and not too noisy. So we'll model the noise across most of the pixel response here by just some sort of base covariance. And then what we're really interested in doing is capturing the way that the covariance rolls on in these extreme values. And here you can see the covariance maps that we've built out of studying the CRF associated with effectively quantizing where the linearity of the camera response dies. And so we get these very high covariances that occur right at the limits. All right, so that covers the noise models that we've used. What we do then is we simply use Kalman filter theory. This is actually a linear system, so it's an actual Kalman filter. And the Riccati equation is scalar, and so the Riccati equation itself is just this equation here on the left-hand side, and it's in continuous time. It's a continuous time system. The Riccati equation is continuous time. And the interesting thing is that because events only occur irregularly, and the way the noise model is built, we can actually solve the Riccati equation in the inter-event periods exactly here, and then we can do updates during the at the point where the events occur. So we're actually solving this Riccati equation for these noise models exactly, and generating a time varying output of the Riccati covariance estimate. So then we take that gain here, the PR to the -1 is the new alpha that we're going to use, and we simply put that into our complementary filter structure, right? And that's all we're doing here. It's not quite the same form as a complementary filter that with a constant gain, and the reason is because the KT here is time varying in real time, but this is just a scalar system, and again we were able to solve it exactly. So the exact solution to that system is what we've written here on the right hand side. And interestingly enough, this solution is not transcendental, so we no longer have an exponential in that solution. So we only have a 1 divided by t minus tp here. That is like a term that dies away, like an exponential would die away. And again, you get the update when the event occurs. You simply get an update of the same sense as what was there before. So complementary filters running. Let's just quickly talk about the de-blur algorithm. So firstly, the de-blur here, we just use a double integral algorithm that was developed by Leeuwen Pan and co-authors, and that works extremely well in the exposure period. And then in the inter-exposure period, we do a simple frame interpolation where we look at the actual value of the intensity that we obtain and the value of the intensity we obtained beforehand, so the two frame intensities, and then we simply scale the magnitude of the events that we're going to deal with, so that the interframe displacement is or change in intensity is matches between the true intensity and the events, and that sort of stops us getting when we do direct integration, it stops us getting some of these fringes that are occurring. So what we're doing there is we're using the information of the events to shape the interpolation, but not as absolute information, and that's because there's often events missing in bits and pieces. So that algorithm we applied to the DSEC algorithm, and these are the results, and we can put this video up on YouTube. This column in the far left is just the camera. Sorry, I'll run that again. So I shouldn't draw on the scene, obviously. Let me just try that again. There we go. I won't draw on it this time. So on the far left of the two left panes is the actual output from the camera. In the top middle is the E2VID algorithm run just raw on the data. So I accept that there would be ways of improving that, obviously by retraining and being a little bit more careful. We're running ECNN in the top right, and ECNN is a smaller, lighter algorithm, so it's not as heavy as the E2VID, but it is also trained on a much wider range of event information, so it's a little bit more robust to different event situations. You can see it's able to pull a little bit more out of the scene, but has its own problems with noise. Bottom middle is the complementary filter that I did with Cedric Schierlich a few years ago, and so that's doing a reasonably good job, but you can see that the actual quality of the asynchronous filter, which is in the bottom right there, and if I can pause, well, I've showed you a couple of those scenes earlier, but you can see that there's a lot more texture in the scene. The high dynamic range is very good. You can see that we're able to actually pick out, structure and detailed structure. The lights aren't blurry. The trees are visible. Lots and lots of good properties out of what we're managing to do. So we're pretty pleased. All right, one last thing in the algorithm, just to show you quickly, is the idea of this kernel that I mentioned before. So we've got the spatial convolution kernel here that we can throw things into, and so effectively you convolve the low frequency events, low frequency frame data, just use the convolved version of that, and then you convolve the events to generate these convolved events, so multiple events, which is an established idea in the literature as well. And so just to show you some data out of that, we've got Gaussian blur in the top middle, we've got a Laplace operator in the top right-hand side there, and then bottom left is an y-axis Sabel, middle bottom is an x-axis Sabel, and the bottom right is a color-coded image gradient that we've computed from the two gradient derivatives. So certainly by throwing the gradient, the kernel operator in there, then we can do linear filtering, spatial linear filtering of the image from linear temporal filtering of the event stream. So it's pretty cool. It's a nice little framework. So conclusion, the ideas that we exploit the asynchronous nature of the sensor with the algorithm design and implementation. So that's a key part of what we're doing. We use both frame and event data, and in a recent talk at ICRA, I was talking about our stereo hybrid event frame sensor modalities that we've been working on. I think that's a very exciting framework to work on, and again, it's working always with this frame data and event data. And I know there's a bunch of manufacturers looking at developing sensor technology with this capability. I'm very excited by these potentials. And the last thing I'd like to say is everything I've talked about tonight is very shallow. I'm absolutely into shallow algorithms. There's no deep learning in anything that we do. That's not just because I'm biased against deep learning, which I am a bit, but at the same time I recognize just how powerful it is. But there's a principle in event cameras that I think is really worth saying, and that's that we're at a period where the quality of event camera sensors is improving very, very quickly. And so you shouldn't be looking as a researcher at event cameras as something that you need to just get good data from for this particular sensor, right? We should be looking at algorithms which work for any sensor and will work better and better as the quality of event camera sensors improves, because in a few years, event camera sensors are going to be bloody good. And these algorithms that I'm talking about here, I believe, will simply go on working better and better and better as the event camera sensors improve. So that's the conclusion. My thanks to my co-authors for this paper, which is Yonhon, Cedric finishing up, but still a part of this, and Ziwei Wang, who's been integral in all of the work that I've done tonight. Thank you very much, and I'll see you at the conference.